Okay, well, good morning, everybody. So the first thing I want to do is just note that your homework from last time is just laying up here on this front table. They're not in any particular order, but please make sure you pick yours up. I do like to at least mention a comment or two, or maybe I should say mention what I saw as major mistakes that many of you were making. But frankly, there really weren't that many. This was all a review homework problem set. So I don't know, a few of you had a little bit of trouble on those first two problems, particularly not really understanding how to get data for a compressed liquid, which can also be called a subcooled liquid. Just keep in mind that if you have a compressed liquid, because we really don't have any decent compressed liquid tables in our book, that you just assume it's a saturated liquid at the same temperature. Okay? Many of you were taking the data at the same pressure. That's not accurate. It's the saturated liquid at the same temperature will give you more or less the same data as the compressed liquid. So just keep that in mind. Other problems dealt with, just ideal gases. Make sure you understand how to use ideal gas relationships or use the appropriate tables. There was an example that dealt with a piston cylinder device. In fact, you had to calculate the heat input, which is essentially identical to what we were looking at now for the diesel cycle, right? It was a constant pressure piston cylinder device heat input type of problem. So that one should have been, that one was important. Shouldn't have had any trouble really with that one. Others dealt with problems involving flow. For instance, there were some problems with a ideal gas compressor that used air, and I guess the last one was an ideal gas turbine that used air. Those are important review problems, not because we need it now, but because we need it next week. When we deal with the Brayton cycle, we're certainly going to be dealing with air compressors and air turbines, and we need to understand how to use both ideal gas with constant as well as with variable specific heats. I might also note that some of you seem to have forgotten the little asterisks I put on the problem statement that specifically requested you to use variable specific heats for certain problems, regardless of what the actual problem statement was in the book. So I know it was a minor error, but still I wanted to note that. You should do it both ways if you can, just so you understand how to use both methodologies. And then lastly, let me just explain my grading. I've got 45 students in this class and more than 30 in other classes, and I don't have time really to write out huge numbers of comments and figure out a very, very exact grade. But I look at all the problems. I go through every page. You'll see little red check marks or dots or whatever that I've put on the page just so I looked at it. And if I were able to identify a particular problem, then I would have noted it on there. But generally, just look at the homework solutions that are posted to see, an appropriate solution. But again, with regards to the grades, a plus would be considered full credit, 3 points out of 3 as it appears in my notebook. A check is 2 points out of 3. And a minus would be 1 point out of 3. And if you just don't turn in anything, or you only do like 1 or 2 problems, well, that's just 0. You can get a plus and still not do all the problems. If you had done all but say 2 of the problems and you did them more or less correctly, your methods were pretty much accurate, then you'd have still gotten a plus. But if you don't do 3 problems or more, then you'd probably drop down to the check range. Or for that matter, if you seem to show that you have some difficulty with some of the problems, maybe quite a few of your problem-solving methodologies are not quite accurate. Or you have a lot of math errors or unit errors or something that are consistent throughout a lot of the problems, then I might give you a check instead of a plus. And then a minus, of course, would mean like you've done like less than half of the work, or you have serious difficulty with many of the problems in the statement or in the problem assignment. So you can kind of figure 80 to 100%. I'll call that a plus. Maybe 50 to 80% is a check, and less than 50% would be typically a minus. So at least now you know where my grading is coming from and what your plus means. Essentially everybody got pluses except for a few students that seem to have missed some of the problems on the homework set. Then you got checks. I didn't give any minuses on this one. A couple of you got zeros because you just didn't turn in the assignment. So, all right, then one other thing to note at the beginning. Last time as I was discussing the example problems for the for the Otto cycle, clearly I was having a couple of issues here and there. And I finally realized it all stemmed from one thing, that the compression ratio is V1 over V2, not V2 over V1. And in my mind, I kept looking at the board and I I think, copying pretty accurately from my notes, but I just wasn't getting the right looking equations, and then I finally figured it out. But I hadn't figured it out earlier as I was going through the first example. And as far as I could tell, I think there's only one typo, if you will, that I put on the board, or at least one that I didn't fix. If you go back to the final process from 3 to 4 for the ideal gas with the constant specific heats solution to the Otto cycle problem, I had basically showed this equal to 1 over r raised to the k power. But no, it's r, right? V4 is the same as V1. That's the maximum volume, the volume at bottom center. V3 is the same as V2. That's the minimum volume, the volume at top dead center. So this should have said r, but in your notes, I put 1 over r. So please just correct that in your notes from last time. There were a couple of students who came up to me right after class and wondered if I'd made a mistake, and indeed I had. So again, something for you to fix, please, in your own notes. And with that, let's get back, to the diesel cycle that we're beginning to look at. And in fact, even before I do that, let me give you a bit of a review of just internal combustion engines in general. Now that we've seen something of the problem-solving methodology, first we understand that in this class, our internal combustion engine is nothing more than a single piston cylinder device. In the real world, you got multiple cylinder engines, but in this world, our ideal thermodynamic world, we're just looking at one piston at a time and one cylinder at a time. If you have a 4-cylinder engine, then they're all identical. You just multiply all your results by 4, or if it's a 6-cylinder, multiply them all by 6. But in this class, we're just looking at one cylinder at a time. We understand also that we're not dealing with any intake or exhaust processes, right? There's simply air within the cylinder, and the piston is alternating between work input, work output, heat output, and then the whole process just repeats, right? So the work input would correspond to the compression of the air, right? The heat input would be, well, obviously the heat input. That's where the combustion process would take place in the real world. But in our world, we're just assuming that there's heat transfer added to the air equal to the amount of heat that would otherwise be liberated by the combustion process, right? The third process is the work processes. This is where the high temperature, high pressure combustion gases, or again in our case, air, is simply forcing the piston downward. So that's our work output. So that's the third process that we'd be dealing with. And of course, in a real engine, that motion of the piston is connected to a connecting rod, and there's a crankshaft. And as the piston goes up and down, well, the crankshaft is rotating round and round, and you connect that via your transmission, ultimately to the wheels and then the tires, and that allows your car to go forward. But nonetheless, we're ignoring all that, right? We're just looking at the work output from the piston. We're also assuming that the work output as well as the work input during compression are ideal processes, right? Adiabatic reversible or isentropic, there's no heat loss, et cetera, et cetera. But then, of course, the final process would be the heat rejection process. This takes place when the piston is at bottom center. And it doesn't matter whether we're dealing with a diesel or an Otto cycle, the heat rejection always takes place at bottom center. Now, in the real world, when you get to bottom center, you simply open the exhaust valve and let that gas escape out into the environment. But in our case, there's no valves, right? At the end, the air is simply cooled. However much heat would be liberated by expelling the exhaust gas into the environment would essentially be the same as what we're assuming to simply be heat rejected from the air at the bottom of our cycle, after expansion or work production ends, and then before the next compression process, okay? And then lastly, I just want to remind you that the Otto and the diesel cycles are different in the way that heat input takes place. Certainly, the heat input begins when the piston is at top dead center, but in the Otto cycle, we're assuming that the heat transfer takes place entirely while the piston is at top dead center. Okay? In the real world, that's never going to happen. You don't stop the engine to let the heat transfer or combustion take place and then start it again, right? It's always moving. So even though we're assuming that it's constant volume, that's not really the case in the real world. However, with the diesel cycle, perhaps it's a little more realistic in that we're assuming that the heat input process begins at top center, but it doesn't complete there, right? It actually starts pushing the piston downwards while the combustion process is really taking place. In other words, there's going to be constant volume heat input, but then, there's not going to be constant volume heat input. We're beginning combustion, or again, heat input when the piston is at top dead center, but the piston is immediately moving downwards, and it's assumed that that process takes place at constant pressure. So the heat input for the Otto cycle is at constant volume, but the diesel cycle is at constant pressure, and that is going to affect our equations a little bit. Also keep in mind that during the heat input process, since the piston is moving, there's work being done, okay? So we not only have work during the isentropic expansion of the gas as we go, let's say, from point 3 to point 4, but we also have work output. Did I say input? Work output not only during during isentropic expansion of the gas, but we also have work output during the heat input process. So that's why we have that P times delta V term in our first law, right? That's the boundary work. That's the work associated with a changing volume. So again, the cycles, while they are certainly similar in many, many ways, they're also different in some key ways, and certainly the methods of solution are going to be slightly different as well. So maybe this little discussion gives you a better feel for the nature of these different types of engines. One last thing I want to note with regards to the diesel engine, it turns out that the diesel cycle is honestly not even the best model for us to use for a real diesel engine. You know, maybe it was 40 years ago, but modern diesel engines are quite a bit different than, let's say, traditional diesel engines. And a modern diesel engine, when the heat input starts, the piston is going to be at about top dead center, so there will be constant volume heat input. But then the heat input is going to continue even as the piston moves. So you're going to have constant volume followed by constant pressure heat input in a more traditional, in a more realistic or a modern diesel engine. And in that situation, we would use what's called the dual cycle. This is very briefly mentioned in your textbook, and as long as I'm just covering random topics here, I would note that the dual cycle, we'd still start at the maximum volume at bottom center. We'd still provide isentropic compression up to 0.2, but now we'd have heat input in 2 steps, partially at constant volume and partially at constant pressure. And then we would go through the isentropic expansion to 0.4, and then ultimately the heat rejection from 4 to 1. So this is called the dual cycle, and it's really a better model for a diesel engine. Okay. However, this is not a model that we're going to cover in this class. Certainly the author could have gone through the dual cycle in more detail if he wanted to, but you know, it's not something that typically is done in a first course in thermodynamics. So I just wanted to point that out. There is a better model for the diesel engine, but we're still using the diesel cycle. That for us is a decent model. Is it great? No, but it's certainly decent. Anyway, any questions on any of this? All right. Then let us just go back to where we were last time, and now we start the new material. And keep in mind, we're talking about the diesel cycle. If I were to show this on a PV diagram, it would look like this. Certainly all this is in your notes, right? So this is our basic diesel cycle. Last time I developed various equations associated with the diesel cycle. You should already have these in your notes: the heat output, the heat input, the net work associated with the cycle, and then even the thermodynamic efficiency, right? We found that this was just 1 minus U4 minus U1 over H3 minus H2. So hopefully this equation appears in your notes. And now what I would like to do is just remind you that all the equations that are in your notes now, everything we discussed last time, applies to the diesel engine, I should really say the diesel cycle, when we have a situation of variable specific heat. So really what I should say is if we're using variable specific heats as our method of solution. Now, what if we don't have variable specific heats, right? We know that we have 2 methods of solution, one constant, one variable specific heats. So what would the equations look like if we did have constant specific heats? So let's just look at that real quickly. Okay. So if we had constant specific heats, well, let's just look at each of the various equations in turn. if we just start with the work input, and I'll just write these on a per unit mass basis, we know that the work input is just U2 minus U1, but with constant specific heats, the internal energy change is CV times delta T. So this is just going to be CV times T2 minus T1. If we look at the heat input term, then the heat input term, well, we saw last time that it would be the internal energy change plus the boundary work, right? W sub B, in case you didn't know what that meant in your notes from last time, is boundary work. In other words, there's going to be the internal energy change plus pressure times change in volume, and we just combine for a constant pressure process, which is the heat input process, right? We just combine the boundary work with the internal energy change, and that gives me the enthalpy change, and therefore the enthalpy change is now Cp times the change in temperature as we go from 2 to 3. So just T3 minus T2. Okay, so that's our heat input term. Now, some students have already come up to me and says, well, why are we using CV for certain parts of the problem, and why are we using CP for other parts of the problem? Well, CV and CP only have to do with the relationships to the other properties, internal energy and enthalpy. We can look at your first introduction to internal energy and enthalpy and specific heats, and it should have been really clear that the internal energy change is simply CV times temperature change, and an enthalpy change is simply CP. It's not like we're mixing anything up here. If you have enthalpy, then you use CP. If you have internal energy, then you use CV. There's no other questions about it. And for those of you who weren't in my class, because I tried to pound this into your heads every week, the fact that we're using the word volume and pressure and even the words constant, some students might think, well, then these are only usable for constant volume or constant pressure processes. That's absolutely untrue, right? These are called constant volume and constant pressure because of the way that they're defined. They're defined as partial derivatives. For CV, it's the partial derivative of U with respect to T holding V constant. So that's why we call it specific heat at constant volume. And CP is defined as a partial of H with respect to T holding P constant. So that's why we call it specific heat at constant pressure. It has nothing to do with a constant volume or constant pressure process. They're simply thermodynamic properties, and we have to use them appropriately, right? Internal energy change, enthalpy change, we use CV and CP respectively. So please make sure that you understand those basics. Let's continue. What about the work output now? Well, we know that the work output is in two places, right? It's the work output during the heat input process from 2 to 3. So this is just going to be the pressure times the change in specific volume from 2 to 3. So this is the constant pressure boundary work term, right? But then we have the isentropic expansion as we continue from 3 to 4, and that's just going to be, well, it's isentropic, so it's just going to be the internal energy change. Again, there's no work terms during that. There's no heat transfer terms during that process from 3 to 4. So we would just say U3 minus U4. All right, so we have work output in two places. And then as far as the heat rejection or heat output, the fact is we really don't even need to use this for most problems. But still, heat output is done at constant volume from 4 to 1. And as such, it's just going to be the internal energy change, so just U4 minus U1, which therefore means that's equal to CV times T4 minus T1. So these should be the various equations that you'd want to use for the situation where we're assuming constant specific heats. All right, so any questions on any of this? I suppose just for completeness, I might also want to show the network, since that is something that we're going to deal with. When I do subtract the work in from the work out, some of our terms are going to combine. And now, in fact, before I even get to that, I just realized I made another little mistake here. I forgot to turn this into a CV delta T term, right? So this should really say CV T3 minus T4. Okay. Anyway, when we calculate the net work, certainly we can combine certain terms here and there. It's just work out minus work in. So P times V3 minus V2, and then plus CV. And then here I would have the T3 minus T4, but then also we subtract from it the T2 minus T1. So, this is how we would find the net work, just the difference between the work out and the work in. Okay. So, next, what about that thermal efficiency equation? Certainly that too has to be modified so that we can, get rid of the internal energy and enthalpy terms and replace them with specific heat times temperature terms. So, now I'm just going to go through a brief derivation. First of all, we're just going to turn the internal energy change into CV delta T. And we're going to turn the enthalpy change into CP delta T. So this would be the basic form of this equation. Now, this isn't the form we want to leave it in. I'm really going to try to generate a simpler form. You may recall that when I did this for the Otto cycle, we ended up with an equation that was only a function of the compression ratio. So hopefully we'll be able to find another term, another version, I should say, of the thermal efficiency equation that's perhaps also going to be in terms of just the compression ratio or maybe some other terms that have nothing to do with the actual temperatures. So that's really where we're headed. So let's just fiddle with this a little bit. First of all, I'm just going to move the CV into the denominator. And this is then going to be just a CP over CV in the denominator. And then I want to do something similar to what I had done for the Otto cycle derivation, and then just factor out a T1 in the numerator and a T2 in the denominator. So we basically get T1 times T4 over T1 minus 1 in the numerator. And in the denominator, we have a T2 then times T3 over T2 minus 1. So now we have this particular equation. And now what I want to do is define a new term that we're going to have to utilize. And this is called the cutoff ratio. And we use R sub C for cutoff ratio. Please don't confuse the subscript C with the word compression. R, without any subscripts, is our compression ratio, right? So that's just V maximum or V minimum. This is called the cutoff ratio. And it's simply defined as the volume at the end of the heat transfer process divided by the volume at the beginning of the heat transfer process. So V3 over V2. Okay, so that's how we're going to define the cutoff ratio. In fact, since it's a definition, I'll just put my third line in the equal signs. Now, just so you know where that word cutoff comes from, let's remember that in a diesel engine, the fuel is injected through a fuel injection process, and that begins at top dead center, and it's going to continue until that fuel supply gets cut off. Cutoff ratio, right? At what volume is that fuel supply being cut off? Well, that's point 3, right? At point 3, combustion has to end because there's no more fuel going into the engine. Now, again, we're not dealing with combustion processes, but still, we're going to understand that the fuel gets cut off at point 3, so that's where heat transfer ends. So, V3 over V2 would be the volume ratio at the end of the fuel injection process over the beginning of the fuel injection process. If you will, it's the volume at the end of heat input divided by the volume at beginning of heat input. So this is simply how we define our cutoff ratio. Now, let's keep in mind that we're dealing with a closed system, a system of constant mass. So if I divide numerator and denominator by mass, I just simply end up with the specific volumes. And then also, I would remember that, well, we do have ideal gases, right? So PV is going to equal RT. So this is also going to equal, well, for V3, we'll just replace it with an RT3 over P3. And for V2, we're going to replace it with an RT2 over P2. Let's keep in mind that R is just our gas constant. It cancels. Let's also keep in mind that it's a constant pressure process from 2 to 3. So P2 and P3 are the same, so they cancel. So it turns out that the cutoff ratio is not only equal to the ratio of volumes at the end versus the beginning of the heat input process, but it's also equal to the temperatures at the end versus at the beginning of the heat input process. So that's our cutoff ratio, and we are actually going to have to use this when I finally make some more modifications to that thermal efficiency equation. Okay, so we'll get there in just a minute. All right. Next, let's look at the following, and I'll just call these notes because frankly this is something we've already seen. We know that we have an isentropic compression process from 1 to 2, so we know that the temperature ratio is equal to the inverse volume ratio, in other words V1 over V2 raised to the k power. Okay, this is just one of the things that we understand. I'm sorry, k minus 1 power. Okay, and today I'm not going to make the same mistake that I did last time. V1 is the maximum volume, V2 is the minimum volume, so this is directly equal to the compression ratio to the k minus 1. So this is something that's going to be ultimately plugged in over there to the efficiency equation. In fact, this is as well. I mean, here's the T3 over T term, so we're going to ultimately replace that with a term that's really only based upon volumes. Here's the T2 over T1 term, right? T2 is there, T1's over there, so the inverse of that is this, so that's going to get plugged in there. Let's also look at the process from 4 to 1. So we would note that T4 over T1 is equal to the following. Now, this derivation is not something you've seen before. Certainly you've seen the equation above before. This one, let's just sub in the ideal gas equation again. So we know that PV equals RT, so P4 V4 over R in the numerator, and then P1 V1 over R goes into the denominator. Now again, certain terms are going to cancel. The R term is going to cancel. Also the process from 1 to 4, really 4 to 1, is a constant volume process, right? So V1 and V4 are the same, so they cancel. So this is just P4 over P1. Now here, I want to divide numerator and denominator by P3. So I get P4 over P3 over P1 over P3. However, let's note that P3 and P2 are the same, right? Constant pressure heat input from 2 to 3. So we can just replace that with a P2. And then let's just keep in mind that the process from 3 to 4, as well as the process from 1 to 2, are isotropic processes. So we can use relationships, well, like the one, is it still over there? Yeah, the one I fixed first thing today. We know that there's a relationship for isentropic processes between volume and pressure ratios. So P4 over P3 is just V3 over V4 raised to the K. And P1 over P2 is just V2 over V1 raised to the K power. Let's also note that V1 and V4 are still the same. So they're going to cancel out of that equation. And this now gives me V3 over V2 to the K. So V3 over V2 to the K. And isn't that the cutoff ratio? Yeah, V3 over V2 is what we just defined as the cutoff ratio. So we're just going to call this RC to the K. And that really is the last term that we're going to have to plug into our efficiency equation, right? We now have T4 over T1 right there, T3 over T2 right here, T2 over T1 up there. And of course, Cp over Cv is just the ratio of specific heats that we call K. So all these terms then get plugged right back in to the efficiency equation. This one goes in there. This one goes in there, and this one, how about that? That's going to go in there. You'll see where they go when you review your notes at home. So anyway, what do we get? Well, first of all, you can see all the temperature terms disappear, and the only thing that's going to be left are terms that are based upon volume ratios, and that's what we really wanted to find. So plug into the efficiency equation above, and what do we get? Okay. So first of all, we have our 1 minus. Now, in the numerator, we'll just have that T4 over T1 minus 1 term. So that's just going to be the cutoff ratio raised to the k, and then minus 1. And then in the denominator, well, I show this as T1 over T2, but you could just move the T1 into the bottom of the denominator. So it really becomes T2 over T1 in the denominator. So that's just the compression ratio to the k minus 1. And then we have the then we have the Cp over Cv term, which is just our ratio of specific heats, k. And then we have our T3 over T2 term, and that's just the cutoff ratio again by definition. So our cutoff minus 1. And there's our equation. So this then is how we're going to find the thermal efficiency if we have a diesel cycle and we're assuming constant specific heats. So are there any questions on this? I mean, please note, I'm not one to ask you to go through derivations on exams or anything like that. But that doesn't mean I just wanted to present this equation and let you try to figure out where it came from. It's an important equation, and it was worth the 5 or 10 minutes I spent deriving it. Now, one other equation of interest to us, and this has to do with the process from 3 to 4, our isentropic expansion process. So one more equation of note. So again, this has to do with the expansion process from 3 to 4. What I would like to do here is note that if we go from point 3 to point 4, it is isentropic. So we would like to look at the volume ratio for this isentropic process. This is something that we will use during problem solving. In other words, at some point, you're going to go through your cycle, and you're going to go from 1 to 2 to 3 to 4. We know 1 to 2 is isentropic. We know 3 to 4 is isentropic. We're just going to look at an equation for the isentropic process from 3 to 4 that we've never quite seen before. And again, the purpose of this is to derive a simpler version of the equation that would allow us to go through the problem solving a little more quickly. So first I would note that I'm just going to take and multiply and divide by V2. So I'm going to put V2 over V3 and then V4 over V2. So again, all I've really done is multiply and divide by V2, so that changes nothing. Then I would simply like to note that V1 and V4 are the same. And now hopefully you can see that that's really just the ratio of the compression ratio to the cutoff ratio, right? I can rewrite this if I want to. I can just write this as V1 over V2 and then call this V3 over V2 into the denominator, compression ratio over cutoff ratio. Okay, so this is another equation that's going to be useful to us. And as I go through an example problem, you'll see that we will have to use this equation as we go through this isentropic process. So really, there's no more equations now to discuss. I think what I'd like to do is just go through an example of a diesel cycle. Now, I'm going to go through the example for variable specific heats. If I have time, I'll also go through the example assuming constant specific heat, but we'll just see if we have enough time. So I'll leave the diagram. By the way, just so this is clear, this equation that was derived just in general. There's nothing that says that this only applies to ideal gas with constant specific heats, even though we had been talking about ideal gas with constant specific heats all the way up until this point. This applies for any process. So please keep that in mind. This applies to constant or variable specific heats. All right, so let's go through an example problem. So let's look at our typical air standard diesel cycle. And let's say we're given a variety of information. So the kind of information we're given here is similar to the kind of information we would have been given for the Otto cycle. So let's say that we're given a compression ratio of 17. By the way, diesels can have much higher compression ratios than gasoline engines. So it's not uncommon to have, a number in the mid to high teens for a diesel, but for a gasoline engine, usually it's less than 10. Nonetheless, we're given the compression ratio in this particular case. We're also told that at the beginning of compression, we know both the temperature and pressure. So the temperature is 50 degrees Fahrenheit, and the pressure is 14 psi. Okay. Let's also be given that the maximum cycle temperature is 3,500, and this is going to be in Rankine. And we're going to find the same things that we found previously. That is for the Otto cycle example. So let's find pressure and temperature at all state points. And let's also find the thermodynamic efficiency. And in fact, we know that we're going to have to use the cutoff ratio. Well, maybe we don't know, but it's a pretty good guess that we'll have to use it. Otherwise, why did I talk about it so much? So why don't we also find the cutoff ratio for this particular process? All right. Now, the first thing I would note is that unlike the Otto cycle example where I simply said, P1 is this, T1 is that, T3 is that, et cetera, here I'm just using words. You're going to have to actually set up problems where you're just given words and you're going to have to turn them into actual, thermodynamic properties at particular state points. So maybe this will help you, try to formulate problems. Nonetheless, the first thing we want to do is illustrate the problem. Again, the PV diagram is already up here, so there's no point in redrawing that. Let's note that we're given the compression ratio. So R is 17. Let's also note that at the beginning of compression, that's 0.1, isn't it? So we're given T1 of 50 Fahrenheit. Now, certainly we're going to have to convert this into Rankine to solve this particular problem. Well, if we use constant specific heats, if we use variable specific heats, we'll just leave it in Fahrenheit because all of our data in table A17 is in Fahrenheit. So maybe I'll just leave it at this for now. We're also given the pressure at that same point, which is 14 psia. So, this would be an engine, let's say, operating in Pomona, right? Here in Pomona, we're close to 1,000 feet above sea level. Our standard atmospheric pressure is not 14.7 like it is at the coast. It's closer to 14. So here's a Pomona problem. And let's also be told, or we're also told that the maximum cycle temperature is 3,500. So 3,500 is T3. Now, that's not a TS diagram, so it may not be intuitively obvious that I've given you temperature at 0.3, but it should make sense. I mean, the temperature is going to be highest when all of our heat input is finished, right? We keep adding heat, the temperature would keep going higher until we finally get to the end of that process at 0.3, and then the temperature is going to start to drop. So T3 is the temperature that I've given. That's the maximum cycle temperature, and that is in Rankine. Okay, and then we're trying to find all those various states and properties, so I'll just leave it at that. All right, so let us solve using variable specific heats. And again, if I have time, we'll do constant specific heats. All right, so first, just a quick talk through the problem. Using variable specific heats, again, we're using table A17 data. We know that in order to analyze the process from 1 to 2, which is isentropic, we're not using equations, right? We're using relative specific volumes, just like we did for the Otto cycle. We know the ratio of volumes from 1 to 2, so that's equal to the ratio of relative specific volumes from 1 to 2. So that's certainly how we're going to go from point 1 to point 2. Once we have recognized that V1 over V2 equals VR1 over VR2, then we just find VR2. We go into our table A17, and we just look up the enthalpy, internal energy, whatever we need. We would use the ideal gas equation of state, just like we did in the Otto cycle problem, in order to find relationships between pressure, volume, and temperature. So that'll allow us to find P2. Then we go through the process of heat input from 2 to 3. This process would require us to use the cutoff ratio. And cutoff ratio will be the relationship between point 2 and point 3, right? T3 over T2 equals V3 over V2, which is our cutoff ratio. So we should be able to find the cutoff ratio and then find the appropriate temperatures at point 3 and go back into table A17 and find whatever other property data we need, like enthalpy or internal energy. And then we go from 3 to 4. Again, it's an isentropic expansion process, so we know how to do that. We'll figure out, we know the relationship between the the compression ratio and the cutoff ratio, right? So if we already know our properties at point 3, then we should be able to use this relationship to get our properties at point 4. And then having that, well, again, we can go back into our table A17 at what will be T4 and look up internal energy, enthalpy, et cetera, et cetera. And then, frankly, we have everything we need, and we'll just solve for the various terms, find all of our temperatures, pressures, our efficiency, et cetera, et cetera. So that's just a quick talk through the problem. The basic discussion, the basic method of solution wouldn't be different if we had constant specific heats. The difference is we're not going to use relative specific volumes, right? We're going to use equations like temperature ratio equals the volume ratio to the K minus 1 power, or pressure ratio equals volume ratios to the K power. We'll use equations to get from point to point during those isentropic processes. So with all that having been said, let's begin this process at point 1. So at T1, we're going to have to go into table A17, and we know the temperature, 50 Fahrenheit is equal to what? We had 459.67. Why don't we just call it 460? And that means we have 510 Rankine. So at this particular temperature, we just go into table A17, and we need two things. We need the internal energy, and we'll just look that up. It's 86.91. By the way, I put A17, but it's really A17E. I mean, after all, you are given data in the British units. The author likes to call it English units, and that's why the author uses an E instead of a B. But nonetheless, this is the data we get, and it's British units, so this is in BTUs per pound mass. And then we're also going to need the relative specific volume, so that we can then go through the next process, really the first process, which is our isentropic compression. So this is 166.74, and again, this is a dimensionless number. Now, while we're at point 1, let's also find the specific volume at 1. So this is just going to be RT1 over P1. Now, R is for air, right? So you'd have to use the appropriate value. There's actually two listed values for the gas constant for air. One would be in PSIA foot cube per pound mass degree R, and what would be in BTUs per pound mass per degree R. The fact that I'm using it within the ideal gas equation of state, and I'm going to have a pressure term with the units of PSIA, means I should really use the version of R, or the term for R that has the PSIA units in it. So this is going to be 0.3704, and the units are going to be PSIA foot cubed per pound mass degree R. All right, so there's the R term. And then the temperature is 510 Rankine. The pressure is 14 PSIA. So we end up with the specific volume at point 1 of 13.49. And the units will be cubic feet per pound mass. Okay, so there's V1. Now, as long as I found V1, let's also note that V2 is just going to be V1 over the compression ratio. So 13.49 over 17. So this is going to be 0.7937. And again, the same units, cubic feet per pound mass. Okay. Now let's go through the process from 1 to 2. So again, we understand that this is a isentropic compression process. We know that the compression ratio is V1 over V2, but it's also VR1 over VR2. We know the compression ratio equals 17, and we've already found VR1. So it's very easy to find VR2. So the relative specific volume at point 2 is just 9.808. Again, it's dimensionless. And now that we have the relative specific volume, well, we just go back into the same table, A17E, and by interpolation, we're able to find the data that we need. So there's really two things we need here. We need the temperature. So you'll find that the temperature is 1507.9. And it is in Rankine. By the way, I think I mentioned a moment ago that temperatures, I thought were in like Fahrenheit and Celsius in table A17, but I think that's not right. I'm pretty sure they're in the absolute scale. Certainly they are in this table A17E. So you are getting the data directly in the Rankine units, so no conversion necessary. Also keep in mind that we're going to need the enthalpy at point 2. We actually don't need the internal energy. Not that we couldn't use it if we wanted to. I mean, for instance, if we were specifically asked for the work input from 1 to 2, then we certainly need the internal energy at 2. But you weren't asked for that specifically. We are going to need the network. At least one way we could solve this problem is with the network in the numerator of our thermal efficiency equation. But the network, at least the equation that I had presented to you and derived, it combined certain terms, and it basically combined a PV at point 2 with the U2, and there's only an enthalpy at point 2 that appears in that thermal efficiency equation. So we don't really need the internal energy. If you would like to, you can do the interpolation and look it up too, or based on the particular problem that you might have, you may have to look it up anyway. But nonetheless, this is going to be 371.27 BTUs per pound. All right, so now we're done with the process from 1 to 2. Let's finish this off at point 2 by, well, using the ideal gas equation to find P2. Now again, we have R already with the appropriate units. We know T2 directly above. We know V2 just a few lines above. So I'm not going to plug in the numbers here. And we get P2 of 703.7 psia. And let's remember that it's a constant pressure process from 2 to 3. So this also equals P3. Okay, so now we're done with that. And now let's go through the process from 2 to 3. And for this process, we're going to have to use the cutoff ratio. So the cutoff ratio we know is defined as V3 over V2, but as was developed earlier, it's also equal to T3 over T2. And this is information that we have, right? So T3 over T2 is 3,500 Rankine over 1507.9. And we end up with a cutoff ratio of 2.321. Okay, so this is one of the things we were looking for. By the way, in case I did not make this obvious, you have to use the absolute temperature scale in this equation, right? We know that already, unless you're using temperature differences, where temperature difference in Kelvin is the same as Celsius, or Rankine is the same as Fahrenheit. We're not talking about temperature differences. We're using actual temperatures in equations. So in, let's say, 99.5% of the time, you're definitely going to have to use the absolute scale, Rankine or Kelvin. Of course, we use Rankine here. All right, so we have RC. And now from that we can find the specific volume at 0.3, because that's just going to be the cutoff ratio times V2. So again, in the interest of saving time, we know RC, we know V2, we just do the math, and we end up with 1.843 cubic feet per pound mass. Okay. And then the next thing that we want to do is go into our property table at T3. And again, we're going to A17E. T3 is 3,500 degrees Rankine. So here what we're going to need is the enthalpy at 0.3. So H3. And again, this has to be found by interpolation. H3 is 938.4 BTUs per pound mass. Okay. I'm not going to keep writing the word interpolation. Hopefully you'll just figure that out. All right. Now there's actually one thing that I also need to do here, and this is to look up VR3. After all, we're going to have to go through an isentropic process from 3 to 4. So don't only look up the enthalpy, also do VR3, and you'll find this is 0.7087. All right, so now we're done with that. We already found the pressure at 3. We knew it was the same as 0.2. So now let's just move on to our final process, which is the one from 0.3 to 0.4. And here we're going to use the relationship that I derived that's actually still here on the board, just this one. So V4 over V3 is equal to R over RC. So 17 over 2.321. Now, I don't really need the actual ratio. I mean, I do need to calculate it, but what I really need is the fact that for this process, again, an isentropic process, assuming variable specific heats, this is also equal to VR4 over VR3. That's really what I need to utilize here, because what I need is VR4 so that I can go into the table and look up the temperature and internal energy or enthalpy. So this is actually equal to VR4 over VR3, which we just found as 0.7087. And therefore, we can calculate VR4 as 5.189. Okay, so here's our relative specific volume. So this is actually how we're going to deal with the isentropic expansion as we go from 0.3 to 0.4. Now, are there other ways to do it? Sure there are. You can use different relationships if you wanted to. There are others that are available, but this is the easiest one to use here. So this directly gives us the ability to calculate VR4. And then at VR4, one last trip into table A17. And here we're going to look up the internal energy at 4, again by interpolation. So this is 341.5 BTUs per pound. And then we're also going to have to find the temperature at 4. So this is 1874.0, and this is in Rankine. And then I suppose, since we're trying to find all of our thermodynamic properties, let's just find P4. So, PV equals RT. So again, we have R already. T4 we just found. V4. Do we have V4? We do. It's the same as V1, isn't it? I mean, I probably should have said that at the time, but you can go all the way back to this first setup in the problem and just remind yourself that V4 and V1 are the same. So we do have V4. It's 13.49. So again, in the interest of saving time, just plug in all the data, and we end up with a pressure at 0.4 of 51.46 psia. So all we've done at this point is calculate the various thermodynamic states, but let's just finish the problem. We're trying to find the thermodynamic efficiency as well. So that's kind of the easy one. So here now, we could certainly just simply use the relationship that is already in your notes. So this would just be 1 minus U4 minus U1 over H3 minus H2. Okay, again, we're not using constant specific heat, so we're just going to leave it in this form. I have U4, I have U1, I have H2. I should have H3. Yep, there it is. So again, I'm not going to bother to plug in the numbers. If you plug in the numbers and go through the mathematics, you would end up with 0.551 or 55.1%. Okay. So there's a pretty complete example problem. I might note that in some problems, you may be specifically asked to find the net work or specifically asked to find the heat input. In that case, just use those directly if you've already calculated them. I mean, we know that the net work input is going to be H3 minus U4 minus H2 minus U1. I'm pretty sure that was derived for you last time. And we also know that the heat input is just, well, the heat input, have we calculated it? No, I guess we never specifically calculated it, but it's just the heat input during the constant pressure process, right? H3 minus H2. So again, you can go through the math. We get 312.7 BTUs per pound mass in the numerator. We get 567.13 BTUs per pound mass in the denominator. And we get exactly the same result. Sometimes it's worthwhile to use alternate equations and see if you get the same answer. It certainly would be nice here. I mean, if you're not completely sure that you have the right answer, well, use a different equation and see if you get the right answer. So just to check your own work. And of course, you can see that these equations are the same, right? I mean, the H2 and H3 over H3 minus H2, that's where the 1 comes from. And then all you're left with is a minus U4 and a minus a negative U1, and still the H3 minus H2 in the denominator. So it's clearly the same equation. So nice complete problem. Now, I'm pretty sure that in 6 minutes I don't have time to do this with constant specific heats. But let me just summarize anyway. Some of you may want to just go ahead and try this with constant specific heats just to get a little more practice on these cycles. So let's just briefly talk about constant specific heats. Okay. First noting that we're not going to get the same answer, right? We know the answer is going to be off. It might be off by a lot. It's hard to say. Nonetheless, if we go through the process, again, we would go through the isentropic compression process. Let me just call this brief summary. But the first process is going to be from 1 to 2. So if we go through the isentropic compression process, we just use P2 over P1 equals V1 over V2 to the K, which is just R to the K, right? And if we use this appropriately, again, I'm not going to go through any of the math at all. We would just find that P2 is 739.2 PSIA, which is going to equal P3. So certainly that number is in the same ballpark, but it is off by about 5% or so. Let's also find the temperature. We would know that T2 over T1 is just V1 over V2 to the K minus 1, or if you will, R to the K minus 1. So if we solve this problem, noting we're already given T1, this should be 1584 Rankine. So again, it should be similar, but it's certainly not going to be identical. Again, we're off by about 5 or 6%. And continuing, we'd still have to utilize the cutoff ratio. We already know what the cutoff ratio is, so we could just use the fact that the cutoff ratio is T3 over T2, and this would then allow us to find T3. By the way, the cutoff ratio is not exactly the same, is it? Because our thermodynamic states are all a little bit different. The cutoff ratio is still going to be, V3 over V2. It's still going to equal T3 over T2, but T2 is a little bit different now, right? It's 1584 Rankine. It's not 1505 or 1507, what we found over there. So we'll definitely get a different value of the temperature, although we're given that temperature anyway, so it's not like we actually have to go through this process. But still, if you wanted to, you would find that you get exactly the same number, 3,500. But nonetheless, I'll just note anyway that that's a given. Now we'd have to go through the isentropic expansion. So T4 over T3 is going to equal V3 over V4 raised to the k minus 1. Please note that V3 over V4 has to utilize the relationship that we talked about over here, although I've now inverted it. So this is going to be the cutoff ratio over the compression ratio to the k minus 1. Previously I had V4 over V3. Here's V3 over V4, so we've just flipped it. But nonetheless, this allows me to find the temperature at 4, and we get 1547.6 Rankine. Okay. We'd also need to find the pressure at 4. Probably the easiest way to do this is just to recognize that we've still got isentropic expansion. So P4 over P3 is V3 over V4 to the k power. So here, the only unknown we're going to have is V4. P4, not V4. V3 we know, V4 we know. Remember, V4 is equal to V1, right? P3, it's the same as P2. So anyway, we go through our math, and we get P4 of 42.5 psia. And then lastly, we can find the thermodynamic efficiency. And since we're dealing with constant specific heats, we're just going to use that one relatively straightforward version of the equation. You know, the one that has that has compression ratio and cutoff ratio. So 1 minus, and then we have the cutoff ratio to the k minus 1 in the numerator. And in the denominator, we have the compression ratio to the k minus 1, and we have the ratio of specific heats, k, and then the cutoff ratio minus 1. Anyway, we have all these numbers. Just plug them into the problem, and we end up with, where'd it go? It's hiding. Oh, here it is, 0.613, or 61.3%. Now again, the numbers are certainly different, right? Previously, we found that the thermodynamic efficiency was only 55%, and now we're up to 61%. Different methods. Certainly, variable specific heats is more accurate, and if you're trying for accuracy, then you would use that method. In this class, of course, you should know how to do both methods. Anyway, so this is just kind of a summary. You could go through it in more detail on your own, and that's all the time we have for today. So have a good weekend, everybody. And I will see you all on Monday. Any questions?